So welcome everybody here. We're going to do open final review. Ultimately, in a few moments, I will say, give me your questions. We'll make kind of a list of questions to guide us um, in a bit. We won't necessarily get to all of them. You can in an hour and a half or however long we go here, we probably can get to a handful of questions. I like to, when we look at the questions, also tour through the exams and peek at a few other things. Um, But I'm going to say just a few big picture items. And then I'm going to point out a couple things so that when you leave, you have more resources um, to study from. So, first off, let's share this. And if you're someone that's not in my class, welcome, whatever your instructor is saying goes, but it is a common final for Math 126. There's my OneNote. Um, I just shared in the chat. I also will share the exam archive, which I think you can see here. Um, well, first I'll share my materials page. I have review sheets. If you're looking for just a final exam fact sheet, I have that here on that page. You just need to go to final review sheets or final exam material. The department exam archive is here. So there's a few things for you to have open and starting to find questions about what you're dealing with. A few general notes. So are for my students, the everyone is in Kane 130. There's a seating chart within the last module of our Canvas page, which should have your seat. If you're someone that has DRS accommodations, you're in a separate place. Anyways, so check all that out. Tomorrow in class, we'll just take questions as well. You get one sheet of notes, handwritten, front and back. You get your calculator model. The last two pages will be on these topics, so we sort of know that's coming. The other 7 pages will be from these things we've done before. So, chapter 12 and 13 items, lines and planes, surfaces. So, at any point, I can kind of stop and give a recap. But things I'm thinking of are, do we know our vector facts? Things related to cross products and dot products and angles. Do we know how to find lines and planes? Occasionally, there's something small about surfaces. Do we know our surfaces, what a paraboloid is? And then curves. Do we know how to find a parameterization of a curve? So curves, tangent vectors, um, curvature, arc length. These other things are more recent. Chapter 14 is about finding critical points, partial derivatives. So I don't intend this. I could definitely turn this into more talking through the topics, but I'd rather be focus on problems. And then chapter 15 is setting up double integrals. You probably will have something on there, probably something with polar and something without polar. And then this is what we've been doing more recently. Um, So it would be good if you're preparing to work through a couple finals in some detail. It would be good to have done a couple double integrals in preparation. It would be good to have found some critical points, maybe done a couple applied maximin, a couple global maximin. One thing about the final, because you have more time, there's always going to be a page or two that causes some delay or that looks different. And you just have to sort of go, okay, I'm going to set that to the side. When I come back to it, I will write down everything I know. So you have more time to do that. So that's also true when we're looking at old finals. Oftentimes, when I have open sessions like this, we find the hardest questions of the last 20 years and everyone leaves in tears. So we will take your questions and I'll look at some of those hard ones. But as we're going through, I want to poke around. Okay, last thing I'll say, and then I'm going to switch to your questions. So get ready with particular questions here. So let me say, when you leave this, you may find that you have certain things you want to review. So I have these kind of a few specific videos that are, okay, a brief review of chapters 12 and 13. This is in my final exam archive. I go through a full exam here. I give some test taking strategies. In the discussion board, I've been posting lots of things like this. Like I worked all the way through the spring 25 exam, the winter 23 exam, the spring 24 exam, and then I have tips on how to deal with multiple choice. So there's kind of the four biggest things. Some things are there. If you aren't in my course, then you can find all these things by just going to this YouTube channel and search for whatever you want. So you're saying, I'm having trouble with multiple choice. Done. Tips for doing 126 multiple choice problems. Me doing several from old exams. So this archive has grown big enough that you can pretty much search and you can see me discussing it if you need a how do I think through the problems. Or let's say you're worried about, uh-oh, center of mass, what if that comes up? You can search. And you can see that some of that's 125. Um, so pretty much every problem, I have a lot of stuff there, but you have to like try the problems first on your own before you go searching. Um, that's kind of a key. Okay, so that's the stuff that's there for later if you need it. There's two general questions in the chat. Looks like they're direct messages, so you can't all see those. I'll address those in a moment. Any other general questions before we switch to what I really would like is particular old exam questions and or topics. So questions slash topics to guide us here. And I'd like us to go at least an hour and a half of things of this sort. Some of the problems will take our time. Um, I don't want to feel rushed here. That's my plan. Okay? All right. So we're gonna take about 30 seconds to a minute where you can jam the chat with questions. So there's some things about intersections and lines and planes. And I'm just gonna kind of note things as they come flying in. Um, I'm gonna make this window a little bigger. Then we'll try to see if there's some common questions. Kind of what's bugging people. Parameterization is stated here. 7A, winter 23-7 again. So there's two votes for that. And let's take a look. Spring 24, 5B, and 7. Can we review center of mass? Projections. This is great. Previous reviews, people have been shyer. This is good. Error bounds, absolute maximins. This is winner 25, question 4. The winner 19, question 6, a volume. Winner 25, question 8. Something to do with polar. Fall 22. And we won't do all these. I'm just getting a collection here because it won't be possible. Question 6. Great. Love it. And these, if we don't address it here, you can ask on the discussion board. You can answer it with each other. You could search my YouTube channel. Most questions I've done at some point. Um, if you want a description beyond just the solution. So two questions. The very first question before we get into looking at what's there, Sophia asked, my friends in Professor Nishiver's class, she mentioned triple products. Um, I didn't cover that in class. It's one of the other uses of cross products and dot products. Um, it's not in the homework, so we don't ask it. It's not going to be on our final. Will we have multiple? I think that means multiple. Somebody else is saying, could we have multiple choice questions? We could. Usually that happens on page one, so don't be shocked if it happens. Um, but we can talk a little bit about that in a moment. Let me see what's going on down here. And then I'm going to kind of see where we're at. So most of the questions here are exams in the last 6 years. Winter 25 was listed a few times. Winter 19 was mentioned twice. Question six. So since that person was first, we'll just start there. And then I think we'll come back and kind of assess where we're at. Um, Winter 19 is then mentioned again later. So we get 2 for 1. All right. So let's go look at Winter 19. As we do that, I'm going to tour it. Most people, it seems like this was the main one asked. Let's go Winter 19. If I ever am looking at a question and it's not the one you intended, let me know. I'm going to make it, I think you can adjust size on your screen, but hopefully you can see that okay. So here we go. Let's kind of scroll through. We're trying to get to question six. Question one is find the line of intersection of two planes. So I like as I'm passing by these to know there's more than one way to do this problem. In my mind, there's like 3 ways, but my way is to find 2 points. So find 2 points that are on both, and then you can give the equation of the line. So we could come back and do that at some point, if that's one. Give the equation of the plane that contains the line. So just a quick reminder, the moment you see these words, you know your answer is going to look like this. The moment you see these words, you know your answer is going to look like this. Y minus Y naught. So here's my quick review of lines and planes. I'm sure we'll get to do some problems in a bit. When I'm trying to find the equation, so somebody tell me in the chat, if you're looking for the equation of a plane, what are the two things you need? A point and a normal. So you want a point and a normal. And my advice back when we did this was to always draw the same picture. Don't try to draw it accurately. And then take the information and draw it on there. So if the line is on here, okay, that's helpful. And it's perpendicular to this other plane, so that's the weird one. We'll have to make sense of what that means. And there was a strategy. So there was kind of knowing what you want, and then the other part was the strategy. And the strategy typically was to find two vectors parallel to the desired plane and do their cross product to find the normal. So there's a couple specific things to talk about there, um, but that wasn't the question. So at some point, hopefully, we can do something with lines and planes, whether it's today or tomorrow. Um, but I have plenty of stuff we can go back and look at. So we're just doing a tour. The question was number 6. Nobody asked that one question. Find a vector function that gives the intersection of these surfaces. So this was a chapter 13 type question of how do we parameterize. We had a certain strategy that worked really well if there were circles. So this question is so short, I could just write it right now. Why am I using theta? Let's use t because they wanted a t. T. So I just parameterize the circle. That's not the only way to parameterize the circle, but it's usually the cleanest way. And then you're done. Y is equal to 10 times whatever z is squared. So that looks funny because it's been a little while. We had something like that on exam 1. We had to parameterize and then do arc length. Somebody mentioned that. How do we parameterize? That was that topic. Yeah, if it's not a circle, then there's another strategy, and the other strategy is to, and we could even use the strategy here. So the other strategy is just you randomly pick one of them to be something else, usually t. If I choose z to be t, then that means y is equal to 10t squared. The only issue with this is it's not as pretty of an answer because now we're going to have to solve for what x is. 9 minus z squared, which we're calling t. So you'd have x minus 2 is plus or minus the square root of 9 minus t squared. And you'd have x is 2 plus or minus the square root of. So I would accept either this answer or this answer. They're both fine for me. Those are two different parameterizations of the same thing. Uh, so to answer your question, Danny, somebody else is saying, would we ever see any other kinds of questions involving intersections of surfaces? The intersection of two surfaces is a curve, and so they were a good example of something that a reason another way curves come up. But there's not, I mean, we had the intersection of two planes, but that's kind of a specific one. Um, yeah, I'm going to record this and it will be posted on my um, discussion board, and it will be on my channel. The surface consisting of all points whose distance to the y-axis is 3 times. So this is a translation question where you're going to have to write, this goes back to exam one, the distance from x, y, z. I can't remember if I had this on exam one or something similar, is 3 times the distance from x, y, z to something else. This is how I set those up. And then I had to think about what the question was telling me goes in these spots. So we can actually do this one too, but then I'll never get to question 6. But if I have a point and I want to go to the y-axis, so if you have a point x, y, z, and you walk straight over to the y-axis, what can you tell me about the corresponding point? Somebody in the chat tell me what's the corresponding point that is closest to you and is on the y-axis? What does it mean to be on the y-axis? Yeah, these are both 0. And if it's closest to you, that means it's lined up with your current y value. And so you put 0, y, 0. So this is what I call closest point strategy. So I'm going to find the distance from my given unknown points to the closest point on the y-axis, and then let's do it again. Now I want to do closest point on this place. Well, the closest point, if you go straight over here, that's going to be when y is 0. And if it's the closest point, these other two things are the same. And we have it. So this ends up being the square root of x squared plus z squared is 3 times the square root of y squared. If you square both sides, you get this. And what in the world is that? If you move everything to one side, it looks like it's hyperboloid. If you cover these things up, hyperbola, hyperbola, circle. So I said that we should call this a circular hyperboloid, but no one asked me. And this is not called a circular hyperboloid. What is this one called? Oh, thank you so much. I never get full credit on these exams. It's a cone. It's a cone because this is 0, you get a circle of radius 0. Um, so it is a cone, a circular cone. Oh wait, they gave us options. I made it harder on myself. Eek. Okay, so there's a few things. I think at this point I'll accelerate to try to get to question 3. Find the tangent plane. I feel like I have a pretty good plan for that. Take the partial derivatives, plug in some values. Find and classify the critical points. Oh, I would love to do that question. I've had quite a few people asking me to review how do you solve in an organized way. But there's a clear strategy there. You're going to need the first and second derivatives. You're going to need to do some organized solving. Let's see what this is. Let T be the right triangle. Who's this? Let S be the solid. Find. So this is a volume setup question. There's something unusual about it, like there's an unknown side, but it's about finding bounds, I suspect. So we could come back. But the question was on number 6. So let's see what this one's all about. Someone did ask this, is that correct? Thumbs up if you did. And apologies, I think I made the chat bigger and I never zoomed it back down. So if somebody had turned their hand, put their hand on for the last few minutes, I wouldn't have known it. Dang it. Um, okay, somebody did put thumbs up. Now I can see your reactions. Lovely. Okay, so let's look at this. Find the volume of the solid in the first octant below the surface and above the XY plane. This one, we have a very clear strategy. So let me grab something from my review sheet. Yeah, where is it? I grab something real quick. Final review. Did I not include it here? Oh, I'll grab it here. Class time. Darn it. I did not mean to click away from that. So I will get us back. Apologies. We're here. So I'm going to grab one thing. I'm going to grab this. Final review. Okay. So this was what this is all about. Darn you thing. So I would have something like this in my repertoire of how do I set up volumes? And that's from our final review sheet, but I had something similar in chapter 15. So first, we have this tool called a double integral. And it needs to be handed two things. The first thing it needs to be handed is a surface. And the problem gave me that. And in fact, it said below this and above this, which is good because that's what a double integral does. It finds the volume from the surface down to the xy plane. So the very first thing you would do is this. Everyone good there? And that's what this was saying. We did this over a few days in class. So let's keep going. The next thing you do is you draw the given XY bounds. I think sometimes I called this 2A and 2B, but that's what we need to do. The nice thing about chapter 15 is a lot of, we have a very clear strategy for attacking these problems. A double integral needs a surface and a region. So the next thing I'm going to do is I'm going to draw a region. Now, at first glance, did they give me any XY equations? They're hiding in there. First octant. X is greater than or equal to 0, Y is greater than or equal to 0, Z is greater than or equal to 0. So the only things they gave me were these two sides, which is not enough. And when that happens, I kind of scratch my head and say, that doesn't even make sense as a region. And that's why there was this third step. If the bounds they give you don't make sense, then you need to find when the surfaces intersect. And probably that's where people got stuck here, but when do the surfaces intersect? Well, the two surfaces are Z equals 0 and this. So we're right at step 3. We need to find when these two things intersect. In other words, when 2 minus e to the x squared plus y squared equals 0. So I think it just looks funny, but this is actually pretty short from here. So let's see what we can say about this. So this means 2 is equal to e to the x squared plus y squared. And I don't know what that looks like, so it'd be nice if I could simplify it a little more. Is there any way I could simplify that more? Yeah, we're going to take the log of both sides. And I suspect this is what bothered people, but we've done it. If we can look past the fact that there's a log of 2, I know how to graph this. That will be when the intersection happens. That's when this surface hits the ground. What is that? It's a circle. So this thing we're integrating over is a circle, but it's only the first octant, so it's only here. The only thing that's a little weird is the radius is the square root of the log of 2. So as long as we could look past that, this does illustrate the strategy. So there you go. We did this, this. The only thing that was kind of goofy here was the solving. And now we set up the bounds. And you have three choices. You can do it in terms of x, you can do it in terms of y, or you can do it in terms of an angle. And this one you would I mean, I'd want to do it in polar. It looks like it was perfectly made for polar. Okay, so now we set up our bounds. So it's the integral from 0 to what? Lovely. And then the integral from now, so when you do now we need to know inside, outside, 0 to, here's the weird number, square root of log of 2. And then you have to convert everything to polar. So the 2 stays a 2. The x squared plus y squared is r squared. And then the most important thing is talk like a pirate. R d theta. So that was the problem. And I used that as a moment to illustrate that was kind of the big theme of our chapter 15 questions. Find your integrand, step 1. Draw your region, step 2. Sometimes that required doing an intersection. And then set up, step 3. There is a step 4, which is evaluate, if they ask that. And we could definitely talk evaluation. I'm going to go just one half a step further. So if I was going to evaluate this, I'd want to distribute. I guess you could do substitution now, but the hard thing here is if we don't have the region, it does make it hard to do much of the rest. I mean, if you had like the wrong radius, it's a smaller deduction, but if you did not get a region at all, it's going to be hard to do the next part. Somebody's asking about partial credit. Um, I'll do it. Now that I peek at it, this might not be optimal, but my first reaction was to distribute. Um, and then I realized I have a little bit of integration. There's one integration challenge hiding in there right here. And that's going to require substitution. This I already know how to do, so I really have this desire to split it into two and do the integral of 2r and then separately do the integral of the other. But I think there's too many questions um, for me to get to enjoy integration here, even though I would like to integrate the whole time. So I would do a use substitution here. I realized after I thought about that I could have done the substitution back here and it would have been faster. Let me look at what other questions are. Do we ever have to convert to polar bounds? I think you're thinking about where bounds are already given in a problem, and then you have to change to polar. Any question that says reverse the bounds or convert to polar is really asking draw the region. So I treat those the same. Maybe we'll come across one of those. Those that asked about this question, are we satisfied? Did we hit your points? All right. Then we have a Taylor polynomial question and then a Taylor series question, but those weren't asked. So this is, we did a volume setup. Volume double integral. And we saw a few other things along the way. We could go back to those, but I want to hit some of these other things. Is there an exam that got mentioned many times? No, if you integrate or differentiate, you have the same interval of convergence for Taylor's series. There's a question being asked there. So let's now take a look at just seeing if I had a common one. Winter 25, I see mentioned a couple times. Question 4, this is all out of order. And question 6 and question 8. So I'm going to pull up the Winter 25 exam. Apologies if I skipped over you. There's nothing fair here. Winter 25? How do I not have that in my archive here? Well, shoot. Let me take a look here. Final exam archive, Winter 25, it exists. I'm just going to add it real quick to my OneNote. Bring it up to the top. Winter 2025. Okay. And there's multiple choice. And I've worked through a few different multiple choice. Do watch my video. You have to treat these. I mean, what's scary about multiple choice is they might take you a long time, but it's not a guessing thing. Usually, several of the questions are going to be fairly quick. But I think the problem that people have with multiple choice is it's really hard not to guess. And so before I even think about what my answer is, I would write down any facts that are related to this problem. Like I would say, oh, the cross product theory of the parallelogram. I would write a few things that I know, and then I would look at the question. I find that very helpful. But that wasn't the question. This one says, find the equation of the plane that passes through and contains, okay, that's a plane question. This one says, find and classify the critical points. No, it says find first and second partials, not classify. Okay. Okay, so question 4 was asked. I'm worried this was asked just because somebody was like, I want to find a max and min, a global max and min. But somebody asked this one, is that correct? You give it. Yes, great. So these ones require a little bit of a plan. I can see the moment I open this problem that I have 4 jobs to do. Do you know the 4 jobs I'm talking about? There's 4 things to analyze. In general, there's 2 jobs. There's the inside and there's the boundary. The reason I'm saying 4 is because there are 3 boundaries. How do I know that? Because it says triangle. So 0, 0, yep, 1, 0, 1, 2. And the picture is more for me. I mean, I just want to help guide my thinking as I go through this. Okay, so there's our region. Here's X. Here's Y. And then I have a surface above it. So you do not need to draw this picture I'm about to draw. But there's this region that looks like this. And there's some sort of flying carpet above it. We would like to know where you should stand so that when you look up, it has the biggest or smallest. And that can either be at a corner, it could be at a point in the middle, it could be above a point on the side. So we need to check all the points appropriately. So if I was just going to diagram out this solution, here are the things that need to happen. Partial with respect to x, partial with respect to y, find when they're both 0. Yeah, I kind if I were a student, I kind of would like global max and min. I know that sounds bad for me to say that, but because I have a very clear procedure for what we're going to do. So yes, it takes quite a few steps and the solutions look bad. But one thing I'm going to need to do is to solve for that. What makes it a global max and min question is at the very end, you're going to plug in and see what makes this biggest. So we have a very focused goal. So then you go through each of the boundaries, and there are three. So let's in no particular order. So a lot of this comes back to describing edges, and we then had to do more of this in chapter 15. So if I was on this edge, what all those points have in common. So if I take an XY point that is on this edge, on this side, then that means that Y equals 0 and X is between 0 and 1. So I need to plug those points in. Let's just, while we're doing this, write the other ones. We also need to describe the green side. The green side is X equals 1 and Y is between 0 and 2. Okay. And the last side is the biggest challenge in the sense that I have to find an equation for that. So what's an equation for that side? Yeah, you can find the slope. I think the slope is 2. 2 minus 0 over 1 minus 0. So it's y equals 2x. Yeah. So number 4 is y equals 2x. So now we have set the table. And maybe just to do the same thing I did with that other problem. So I don't know if this is I'm trying to think of what would add to this. Here, this is what my note sheet would say or have, or some version of this. This is from my review. That's kind of dense. I think I have it written better elsewhere. We would need to find the critical points inside the region. Okay, that's what we're going to do here. Then over each boundary, substitute the XY equations into the surface to get a one variable function. That's the big thing. So for each of these, we need to substitute this in to our surface. So one of them we're going to plug in as 0 for y. The next one we'll plug in a 1 for x. And you get 0 for y is going to make it x cubed minus x. If you plug in a 1 for x, you get 1 plus 2y minus y squared minus 1. And then the last one, if you plug in 2x, you get x cubed plus 4x squared minus 4x squared minus x. So because I'm kind of planned and prepared for global max min questions, I would do all of that as a reflex. So that's what, as I said, as a student, I like these sorts of questions where I'm like, I already know what I'm going to do when I open up that problem. There are details to figure out from here. Questions about setup first. So these problems are a little bit of a journey, but now we know what we need to analyze. And this was more about explaining that, oh man, this is very different in 3D than it was in 2D because there's a lot more boundary points. So we can go through and solve any one of these problems if we like, and then we'll try to figure out what the biggest and smallest z's are out of this entire process. So each somebody's asking, where am I getting this from? I'm getting this from the region. So I'm trying to describe first, what does it mean to be a point on this side? What do those all, we can't plug them all in because there's an infinite number of points. So instead of plugging them all in, we describe them. So if I give you a point from that side, what can you tell me about it? You can tell me that the y coordinate must be 0 and the x coordinate is between 0 and 1. Does that make sense, Danny? Yeah. And then the next one, if I take a point on this side, what can you tell me about it? Well, all the points on this side have x as 1. So this describes points on that side. So we really are just trying to plug in the endpoints. Unfortunately, there's a lot of them. And so we have to be organized about how we do it. And then we have the third side. Okay. Anyways, this for the critical point in here, I would pick one of these two, whichever one looks simpler to me. I would pick equation 2, solve for one of the variables. So I would get 2x equals 2y. I'd get y equals x. Then I substitute that into equation 1. I always make these little trees, so I make sure that I've substituted in. So I need to plug y equals x. I don't know why I wrote 0. Y equals x into equation 1. So 3x squared plus 2x minus 1 is 0. Oh, does that factor nicely? It must, or why would this be on a final? So I'm going to guess that it factors. And let's see, do we want minus 2 and plus 1? No. Why am I laughing about? I don't know why I said that. This should be minus 1. Minus 1. I'm still wrong. One error leads to another. Minus 1 plus 1. I'm just testing it out. I'm hoping it factors. Minus, okay, 2. Okay, I got it. So that was not very elegantly done. But I get two solutions. X equals negative 1 and x equals 1/3. I'm going to just ignore x equals negative 1. Does anybody know why? Yeah, it's not in the region. It doesn't matter what the other value is. Because I would like to also know the why, but because x equals y, that means y is 1/3. So we have just what we really did, took me a few years of kind of teaching calculus to really fully appreciate this. We just ruled out all the points on the inside except 1. So we don't need to plug in any other points on the inside, just 1. And it's the point 1/3, 1/3. That's because the surface has a bump there, maybe. That's where the slope is 0. And so you could figure out what the z value is there. And that's our first candidate. And what is that? Is that a nice number? This is the part that's always takes the longest for me, is just the evaluation at the end. So we need to figure out what that z value is. And by z, I mean this thing. Oh, thank you, Owen. Appreciate it. And I don't know if it's a max or a min or a saddle point. I'd have to do a little more work to figure that out. But the question didn't ask that. So, anyways. So then we go one by one through the sides. So now we're going to do this one variable calculus problem. So on that side, it will be whenever that is biggest. And that can be biggest at an endpoint. So one of the endpoints would be 0, 0. when this is 0 and this is 0, or this endpoint 1, 0, which is when this is 1 and this is 0, or a critical number inside the region. So we need to do a one variable calculus problem, set it equal to 0. We get x squared is a third, and we get x is plus or minus the square root of a third. Okay. Are any of those actually on that boundary? X is positive a square root of a third. So that gives me one more point I need to consider. Positive the square root of a third and 0. We have now completed the calculus 1 problem there. Those are the 3 points you have to consider on that side. The two endpoints and the value. And we need to know what those z values are. I'll do this one because it's fast. 0. I'll do this one because it's pretty fast too. 1 minus 1, and it's also 0. This one I don't really want to do. And then you keep going. I mean, this is, it's a final. This feels better for a final than elsewhere, but all three of those look like I have some work to do. Actually, now that I peek ahead, I'm cheating and looking ahead. This is going to end up being exactly the same as this. Did I do that right? In which case, that actually shortens our work. So we are going to eventually, somebody's asking a question. Why didn't we plug in all three endpoints? At the current moment, we are analyzing, when I was doing this problem, I was only looking at this side, and there's only two endpoints on that side. We will eventually consider this. You will always end up considering all the boundaries. I just hadn't gotten there yet. I would have gotten there on the next side. So this was just referring to this. Yeah. The two endpoints. Okay, so then you go to the next one. The next one, oftentimes I don't, because one of the endpoints of this side is 1, 0. I don't usually write it again because we already did it right here. The other endpoint is when x is 1 and y is 2. You know what I need? A little cheat, something you can't do on the test, is realign your problem so it looks better. Make it smaller. And up here, there, we're in business. Here, there. That was from here. This was from here. This is one of the endpoints here, and the other endpoint we've already evaluated. And so we just need to do this one variable calculus problem, which is take its derivative, set it equal to 0. You get y as 1. So that would give me the point 1, 1. Done with that side. And then lastly, we would do this, but if I did it right, it's the exact same x value. X is equal to the square root of 1/3, plus or minus, but only the square root of 1/3 is there. So on this side, the endpoints I already know. When x is 0 and y is 0, that's already been done. And when x is 1 and y is 2, that's already been done. So the only point I haven't considered yet is this one, which is when x is the square root of 1/3. And since y is 2x, this would be 2. It's not elegant, but the answer is there. At this point, I go, I know I have the answer. Somebody's saying the y value for 1 over square root of 3 will be different for equation 4, though. That is correct. Yes. Just the solving was the same. So I know the answer is one of those. It's not an elegant problem, but if you know, this is why in that class I like to emphasize, if you know from step one that there are four things to do, you can at least separate your work and kind of spread things out. Um, so yeah, there's a lot of calculus that comes together there. Um, but I hope you have a plan now and don't overstudy for that. Just I think there's plenty of other things to study. So that's why in class I'm always like, know how to start this and you'll be doing pretty well. Okay. Spent a little bit of time there, but is that all right? I didn't finish. Sometimes people are like, he never finishes any question. Valid point. Does anybody have the answer for me? I need these other z values. 1, 1 gives me 1. I can do that one. This one I have no idea. 1, 2 gives me 4 minus 4. Is this 0 as well? 1 minus 1. 4 minus 4. It's 0. So I don't know what the other two values are because I'm being lazy. So if I plug this in, I get 1/3 minus 1, which is 2, negative 2/3. How did we get 1 over root 3? I got that by taking the derivative of this. So you have to kind of switch gears to the moment you get your function here. It's a one variable calculus problem, and the maximum occurs for any just curve. The maximum is always either at an endpoint or a bump. Calculus is really good at finding the bumps. You take the derivative and set it equal to 0. So this was me trying to see above this side, are there any bumps? I took the derivative, I added the 1 to the other side, I divided by 3, I did plus or minus the square root. Does that make sense? Somebody's asking me about that privately. Yeah. Okay, I think I'm going to move forward. Have you go to the exam archive for those other two z values. So I'm being lazy. I think this one's going to be negative. So it's probably the minimum. I suspect the other is the maximum. Okay, I'm going to move here and keep going. This wasn't asked, but it relates to a question earlier. Let me know if you want, if we want to stop somewhere. But this question is asking you to reverse the order, but it's really asking you to draw this. If you draw it, that's really what it's about. And this is a good example of something that looks worse than it is. So a few reminders because it's a fairly short question. So let's do it if that's all right. Is that okay? Can we do this one or should we move to something else? I'll see if I can get two replies. Yep, okay, there's two. Um, so the outer bounds are y. I think of those as the tick marks. So whenever I say that, what I mean is this. Y equals e, whatever that is, and y equals e squared, whatever that is, are my tick marks. That's my start and my end. So this problem, everything is in terms of y. So you could make a note on your note sheet or something that, oh yeah, if the y is on the outside, everything is in terms of that. But you also could always, if you ever forgot, you could just write down what this is saying. This is saying that e is less than y, less than or equal to e squared. And based off of that, x is between 2 and log of y. The inner bounds are always your functions you need to graph. So we need to graph two things. X equals 2 and x equals log of y. So when I was a student, I kind of programmed myself of, okay, you're telling me I need to graph the inner bounds. Yes. So if you do that, you probably are going to know what to do in the question. So you have to graph these two things. And sometimes students tell me, well, I don't know what x equals to log of y looks like. And to that, I would say, well, you're not forced to leave it in that form. You know, in a moment, you're going to have to rearrange it. So how about you write it the other way? What is x equal log of y the same as? Y equals something else. This is true like you had yeah, e to the x. This is true you had a homework question like this where there was like an arc sine, but if you immediately rewrote it, you had to be able to graph sine. Now, if you don't know how to graph either of those, I can't help you. I'm joking. Even if you can't graph either of those, you could plug in a few values. Plug in 0 for x, see what you get. Plug in 1 for so there's a lot of things you can do. Graphing is not as bad as it. You just have to practice it as you're doing problems. So anyways, I'm going to graph y equals e to the x. I know that it swoops up like this. And now I'm kind of happy with the way the person, I better draw it correctly. When you plug in 0, you get 1, which is not E, which is down here. I was jumping the gun here a little bit. Y equals e to the x. But let's plug in a few points now that I don't trust myself. Just as a reminder, if you ever are worried your graph is wrong, here's what you can do. E to the 0 is 1. I don't think there's enough realization that you can always plot points. So this is 1. This would be when you're at 1, you're at E. This would be at 2, you're at O. So actually, whoever set this problem up was trying to be nice by using E and E squared. Um, okay, what else do I know that I have not graphed yet? So now I have graphed this. What's the other thing I need to graph? X equals 2. So where in the world is x equals 2? It's right here. Don't try to guess if it's a horizontal or vertical line. Just think about plotting points. Think about all the points where x is 2. 2, 0, 2, 1, 2, 1.7. Oh, that's those points. So this is what I would do like out of a reflex is I would have graphed these two and I would have that picture in front of me and then I would have shaded. And how I know when to shade is where my tick marks are. So I'm going to shade from here up to here. There we go. That's it. And you can even like grab, if you wanted to like check your work, you could grab a point that you think is sort of in there, like 1.5 and E, and you could say, does 1.5 and E work here? Meaning, does it give me a valid inequality? But that's kind of, hopefully you don't have to do that. So the moment I've drawn the picture, now I get to switch gears. So you can see I really take my time. I want the picture to be right because now I'm going to redo it in terms of X. And I'm going to say, well, how is it from there to there? So the tick marks for X are 1 to 2. The function doesn't change. Function looks super weird. And the inner bounds are the bottom, which is y equals E, and the top, which is y equals e to the x. These are the same. Okay, I'm going to leave that. I know that wasn't the question, but can't help myself. Somebody was asking about question 6, though. Is this working? Are we getting a few things done? So I feel like we've hit double integrals. We did max and min. So we've done a little bit of chapter 14 and 15. Yeah, how do you integrate it? Um, because there is no y here, you can even pull all of this out to here. So the advantage of what we've just done is now the inside integral is much easier. I imagine people got kind of stuck after that. I kind of like just asking people to reverse and not integrate anymore because I like to separate the skills. Um, but what you're going to get is the integral from 1 to 2, e to the x minus e times x to the fifth, e to the x minus e. And the answer is yes. If you do a substitution, it's going to come out just right because this is u and this is du. If I was grading this, that might be worth 1 point though, because I want to see the reversing the order. That's the main skill. Okie dokie. Anybody ever had parents that said okie dokie artichoke? Okay, let's look. I think this was a question asked. Did somebody ask number six? Yes, great. Find the volume, and hopefully we can see this. I think I've zoomed in and out a few times. Find the volume of the solid that lies below the cone and above the XY plane and is enclosed by the cylinder. You may find the following. So my first reaction is, oh no. Why are they telling me these identities? Is it a really hard problem? But don't let stuff like that distract you. This fits now. We get to do this same thing. So you know, watching me do problems is really not that helpful, probably, but we need to be putting things together. Control V. So we're back to this again. We did earlier in the session. So I'm going to do things that I can do automatically. I want the volume under this and above the ground. 2 plus success. So that's what we want. The rest of the problem becomes the region. And that's really what these are about. So now we switch gears to the region. So if you haven't caught on any question where you're setting up a double integral, you could basically draw these two things immediately, this and this. And then you're going to fill those in. That's where we always start. So first you put your integrand in, then you draw. And back when we were talking about this, I tried to break it into two ideas. Were there any given equations that involved only x and y? In this case, yes. So this is nice. And the last one we did that was no. They did give me an equation that only involves x and y, and that's a circle. A circle centered at 0, 1 of radius 1. So let's draw it. Here's an example where I don't really need step 3. If my question was, well, when did the surfaces intersect? Never. Why never? Because 0 equals 2 plus the square root of x squared plus y squared never happens. This means this surface never hits the ground. But that's fine because they gave us the region. We didn't need that. So now the stage is set. And the rest of the problem, we are now going to get to cover something we sort of have covered, but this has more to it. So this was really just a polar question. That's what's interesting about it. But I want to make sure that we're getting past that step 1. Cool, we good there? Let's talk about setup now. So we either can do this in terms of x, in terms of y, or polar. There's several things that are pointing me towards polar, but honestly, if you were stuck, you could do it in terms of x or in terms of y. The negative of doing that at first glance is it might be kind of messy when you solve for x or when you solve for y. You'll have square roots. But that would actually be fine. Like if you were stuck here and couldn't figure out how to do this in polar, just do it with x and y. It might make the integration harder. Okay, so I'd like to do it in polar. The only problem is it's not a circle centered at the origin. So the moment I make this choice to do it in polar, I now have some work to do, which is I need to somehow rewrite this. using polar, using the fact that x squared plus y squared is r squared, and x is r cosine of theta, and y is r sine of theta. So we have a little bit of a challenge here of making this happen. Yeah, you already did it. So somebody says, I already did it. Um, I would expand this out simply because then I can see x squared plus y squared. Oh, actually, there's a little more. Oh, Sophia, you're talking about this up here. This is 2 plus r. That is true. But the boundary here is what I'm working with now. So this is going to be r squared, and this is going to be 2r sine of theta equals 0. Yeah, no, you weren't you nothing to be sorry about. You get there, you're doing good. All right, so this is this, but that's still not in a very user-friendly form. In polar, we typically want r equals so that we know the distance from wherever you start to wherever you're going. So this one's kind of funny when you first see this, but you divide both sides by r and you get r as 2 sine of theta. But we have seen this before. Anytime it's a circle that's like off center like this, you get this 2 sine of theta or 2 cosine of theta. So this is not the first time, but that was probably the biggest challenge in terms of converting. If you ever have a polar curve and you're just having trouble making sense of it, the things you plug in are 0, pi over 2, pi. So if I was just trying to make sense of this, I'd plug in a 0 and I would say, okay, that's 0. Okay, that sort of makes sense that when I'm looking this way, I'm at the origin. If I'm looking up, I get 1. So this is at 1. If I'm looking to the left, I get 0. That starts to worry me a little bit, but I'll deal with that later. Yeah, the radius is 2 theta to the edge of the circle there. Okay, there is one thing here that I suspect very few students got right on this final exam because I don't think I would have gotten it right if I was a student. But let's sort of talk from here. So at this point, we want to integrate over this entire thing. I'm going to draw it bigger just for effect here. So if you didn't make this error, you're doing better than me. So as you go here, we now have a formula for how far this is. It's 2 sine of theta. Not as good as my Desmos animation, but there you go. I think if I was a student, I would have been very tempted to do the following. I would say the integral, and this is wrong, I'm going to make a mistake. 0 to 2 pi, and then I would have said 0 to 2 sine of theta, and then I would have said 2 plus r, and then I would have said r d theta. And I would have computed it, I would have handed it in, I would have been confident I was right, and then it wouldn't have been right. So to me, that's really hard to not realize that. Does anybody know why it's not 0 to 2 pi? Ooh, I like pi over 2. When you get, because there's nothing on this side, that means that when you're looking this way, you're actually getting a negative. I actually think I have to, maybe I hope I'm not saying this wrong. I think this comes out to be 0, in which case I would be really scratching my head during the final. Like, what? It's 0? But that's because things canceled off. You actually need to do 0 to pi because it does one full loop. Essentially, this is a loop question. Um, so I suspect that this was the hardest part. So I think what would happen is if you did a 2 pi, you'd get 0, and then you'd be like, I don't know what went wrong. And at that point, I would come back here and plot points. And I would go, oh, from 0 to 2 pi, I went all the way around. What about that one formula, what somebody's asking, where it's 1/2? Yeah, we don't use that. The form somebody's saying about this formula that looks like 1/2 r squared d theta. Is that what you're talking about? Um, that's for the area of a polar region. This is not asking for the area of a polar region. This is asking for the volume above a polar region. So this shortcut formula that you might have used in the homework is only areas. Now, when we did it in class, I never used that because we didn't actually cover it. It's from 10.3 of the text. But you can't use it here because the integrand is not 1. So this only applies for area, not for volume. If for volume, you're back to doing this. When theta is pi over 2, wouldn't the r be 2? It absolutely would be 2. I miscopied right here. This is 2. Doop, eep. So this is 2. Thank you. Yeah. So that's, to me, like I said, the hardest thing would have been, for me as a student, would have been to know that that's not 2 pi. And so I know that if I was a student, I probably would have put 2 pi. I would have gotten 0. And then I would have been plotting a bunch of points to try to figure out why I got 0. Um, but that's a good example of something that if that happened to you, it's you still would be able to do most of the rest. I suspect when it's time to integrate, we're going to get sine squared or cosine squared. And the person who wrote this question was trying to give a hint. How did we get the integral from 0 to pi? So that's what I was talking about with this. Typically, what we're more used to, just a small few comments here, we're used to questions like this, where you would say the interval is 0 to pi over 2, and versions of that. Let's do a quick digression here. If you look at your polar homework, there were three, I think in office hours, I was calling this level 1, level 2, and level 3 polar. So here's our level 1, level 2, and level 3 polar. We first had questions where they basically told you everything, and they gave you this. I don't know, this was 2, 3, and the bounds became 0 to pi over 4 and 2 to 3. Most people are good with level 1 polar. Level 2 polar were these problems where you had like a loop where it hit the origin. We did a question like this at one point. A rose. And in order to figure out when a rose ended, and I'm going to be wrong in doing this, but let's say this is cosine of 4 theta. I don't think that's right. But how did you figure out when a rose started and ended? Does anybody know? How did you find this angle? You had to find when R was 0. So you had to find two consecutive solutions when R was 0. So sometimes you can see the bounds just by rotating and seeing when the angle starts and ends. Sometimes the question was, okay, stop when you get to R equals 0. And then there was a third type you saw in the homework, which was a question that you also saw on the exam, which is what if you have two different polar shapes and in your exam you had a region like this. So in order to find this angle, what did you have to do? So this angle was pi over 2, but on the test, how did you find this angle? You had to take the polar curves and do the intersections. So those are the three levels of finding theta. Sometimes you can just see it from the picture. Sometimes you need to figure out when it hits the origin so you know that when the loop starts and ends. And sometimes when you have two polar curves, you need to find the intersection when the r's are equal. Okay, so back to this question. We need the starting and ending angle. We visually, to me, it looks like we started here And then we were in the region, 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 in the region. So the question is, when am I stopping being? Oh, right here. So visually, it does look like 0 to pi. But because it's an entire circle, I'm very tempted to say 2 pi, because when we go all the way around a circle, the radius is 3, we're used to saying 0 to 2 pi, 0 to 3. And so that's why I'm telling you, as a student, I would have been tempted to write 2 pi. And honestly, I bet, I'm just guessing, my 18-year-old self would have put 2 pi. I would have gotten 0 at the end. I would have realized something is wrong, and then I would have gone and fixed it. So I think I would have been okay. I would have come back and said, why did this happen? And that's when I'd realize, oh, it hit R equals 0. So this is actually like a petal of a rose. Um, so by the time you get to pi, you'll have mowed the entire yard. So if you go to 2 pi, you're double mowing. Not only that, you're getting negatives. Um, so that's how we think about the angle. Where does it start and where does it end? What was interesting about this one was that it started and ended at the origin. I think I'm going to move forward though. It would be fun to look at that shape, but let's keep looking. I know there was another question on this exam. So I think it was 8. Does somebody have a question on 7? 7's an error-bound question. 8 is the Taylor series question. Oh, and 8 is is not allowing you to quote something that I have been doing. Okay, so we can do either one of those. So let's look at this one. This is a full error-bound question. Somebody's saying privately they want to see this. Anybody second that? Yeah, we can do 7. Thank you. Okay, so we're going to play the derivative game. So let's have a little race between everyone in the chat. Um, Based at 1. So I'm going to lay out the thing. You try to beat me. Start taking derivatives. I'm going to lay out my little list here. It's based at 1. Don't miss that. I'll lay out the clothesline here. And the derivatives begin. Okay, so here we go. So my function is log of 2x minus 1. The first derivative is 2 over 2x minus 1, which I'm going to write it in the weird calculus way we write it. The second derivative is negative 2x minus 1 to the negative 2 times 2. A little bit of chain rule work. That's negative 4 over 2x minus 1 squared. And I need one more. The third derivative is, I'm going to make this 4 right now, just so it's easier for me to look at. The negative 2 comes down, it's going to be 8 2x minus 1 to the negative 3 times it to the inside. So this is going to be 16 over 2x minus 1 cubed. So I did some derivative work. And now I'm going to plug in 1 everywhere. I'm going to plug in 1. I'm going to plug in 1. I'm going to plug in 1. So this is f of 1. This is f prime of 1. This is f double prime of 1. This is f triple prime of 1. And f of 1 would be the log of 2 minus 1, which is the log of 1, which is 0. Okay, tell me your coefficients. Just tell me these 3 numbers in the chat. Comma separated list. wasn't a very clear question. I think plugging in 1 gives you a pretty nice for each one of these. So if I plug in a 1 here, I think I get a 2. If I plug in a 1 here, I think I get a -4. If I plug in a 1 here, I get a 16. So I win. 2, -4, 16. Did I make any mistakes? Yeah, great. And if I was going to use this as an approximation, I probably would want to clean it up. But this is approximately the same as 2x minus 1 minus, let's see, 4 over 2 factorial is just 2. X minus 1 squared. 16 over 6 is actually 8 over 3. So plus 8 over 3. Plus or minus some error. Okay. Uh, Not picky about simplifying here. I do want to see you lose points. These are always sad ways people lose points. You lose points if you don't include this at all. And we have to take off points for that. And usually about 10% of the class does that. So don't do that. Um, but I do want actual numbers. Sometimes people will just write the general formula without actually plugging in. So what we're grading here is did you take the derivatives? Did you plug the numbers in? Then it says, you'll see this on a few old finals. It wants you to use this. 16 over 6 is fine, or 16 over 3 factorial is fine. What if it asks us for a high Taylor polynomial? We would never ask on page 7 more than the second or third Taylor polynomial because if you're having to take derivatives, it can take a while. Okay, this is you'll see on some old finals where they say, okay, use what you just got to approximate something. So there is a little confusion here, which is you have to figure out what in the world that has to do with the previous part. Because this doesn't look like that at all. What we just figured out was the log of 2x minus 1. And so if we're going to use the previous part, we have to figure out what we would plug in here in order to make that look like 1.04. So I remember, I don't know that I was teaching that quarter, but I've seen exams like this where the student misinterprets the question as I need to plug in 1.04. And then I take off a point and then I grade based off of that. Yeah, so if you do part this wrong, there would be some credit because it affects part C as well. So I would grade part C based off of what you did here. But you need, in order to start this, you have to figure out when is 2x minus 1 equal to 1.04. And that would be when 2x is 2.04, which is when x is 1.02. Oh, it's 1.02 that I need to plug in. Does that make sense? I mean, the person who wrote this question was trying to see if you understood what we just found. Um, so you have to go, okay, we need to plug in a 1.02 to what we just found. And this is what we just found. And now I'm kind of happy that I simplified a little bit. But I'm going to plug in a 1.02 here, 1.02 here, 1.02 here. And I probably would do calculator work here. You'll notice during these, most of the time, I haven't had a calculator in my bag all quarter, so I went the whole quarter without it. But there are times I probably should have had it. Okay, 2 times 0.02. I find it harder to find the calculator. Um, oh, this should have been to the 1, right? I'm just miscopying. So the answer is going to be this minus 2 times this squared plus 8/3 times this cubed. That's going to be pretty close, I bet. But and the reason it's 0.02 is because I'm subtracting the 1. So if they're asking you to use your approximation, that's what you do. You go, okay, what does this have to do with the previous part? How do I make this value come out to be this? So then the question says, I want you to get a sense of how bad this is or good. So let's play that game. Can we go to C? Questions on previous parts? Clean this up a little bit. Okay, let's go to the last part. So to do the error bound, we now have to just fall into Taylor's inequality, meaning compute the next derivative. So in this case, we need the fourth derivative. Find an upper bound. And then say that the error is less than or equal to this over 4 factorial. So our job is to figure out what this is. There is one little question, you people usually ask me about this, but I'm just kind of laying out, here's what you would be writing no matter what, and you would need the fourth derivative. So let's write that down. Fourth derivative, so it's going to be 16 times -3, 2x minus 1 to the -4 times 2. I think that's negative, let's see, it's 32 times 3, -96. So I'm getting that this is -96 2x minus 1 to the -4. Let's use the absolute values to make it positive, and let's make it look a little prettier. So here's Taylor's inequality. I need to find a maximum of the next derivative. I then need to plug in where I'm approximating, and that will give me a number. So basically, I have two things to plug in. The natural question is, we're missing something. What are we missing that we usually are given? Where is the interval? I've seen students put stuff like that on the test. On the last test, somebody wrote, this was an evil question, and they wrote like drew an evil picture, which I felt bad about. They did not like my bento box question. Um, anyways, yeah, the tricky part here is you have to figure out where it was based. It was based at b equals 1. And we did an approximation where we plugged in 1.02. So that's how far away we got from our base. That's the interval. We actually accept any interval that contains that. Sometimes I've had students make it symmetric, and I've always given full credit for that. But there's our interval. We want to know how much did the graph possibly bend away over that space. Okay, so then you play this game of this will be biggest when the denominator is smallest, which would be when we plug in 1, which actually makes it nice. This is very rarely does M come out nice in these problems, but this one does. because it's 96 over 2 times 1 minus 1 to the fourth, which is just 96. That's pretty big. The graph has a lot of curvature, but 4 factorial is pretty big too. And then the other saving grace is that we're actually really close. Our approximation is not very far away, 1.02. So this is going to be 96 over 4 factorial. This ends up being 0.02 to the fourth. I suspect that's pretty small. You can leave it like that too. All right, how did we do? Okay, so there's a question to go over page 8. I have to remind myself, we've gone through a couple of exams in quite a bit of detail. Winter 2025. There's a question about 8, so I will go look at that. But just for my own, it's hard when I make the timestamps because I have to kind of watch myself again, which is painful experience. Um, and then I have to realize that I did a bunch of problems in the middle and figure out what we did. But I know that if I don't make timestamps, it's really hard to use. All right. So let's look at question 8. We have ranged over quite a few things. I think the main thing, as I think about what we've done, we haven't done that much chapter 12 and 13 stuff. So maybe it'd be good to switch to that in a moment. But let's go look at page 8. So this is still winter 2025. Somebody's asking me. I have sometimes everyone can see the message. Sometimes I get them privately. Um, so this question is a little bit, this is a quarter where the instructors all agreed that these were the only Taylor series students could use. That changes the nature of the question a little bit because I've allowed you to quote others. Um, so there's kind of two ways to do this problem. Doing it with what I've allowed you and doing it with what they were allowing you. So that adds a slight bit of complication. Maybe we should just do it the way I would. So I'm going to add a couple more to this list. Um, this is just good for us to talk about anyways. So let's pretend we add two more to this list. Uh, Negative log of 1 minus x and arctangent of x. So write down what you think those patterns are. One over k plus 1, x to the k plus 1. This is negative 1 to the k. We derived both of these in class. And honestly, all three of these I clumped together. So I'm going to put it over here too. Well, these are the three versions that I put on my little review sheet. Log of 1 plus x is a variation on that. It has alternating sums. It's not quite as clean. So typically the 6 I give are these three, and those three. The reason I like to separate them is these ones have an interval of convergence of everywhere, and these ones have an interval of convergence of x's between this. The goal of page 8 is for you to use those, meaning you don't have to take derivatives or anything. Using the machinery there, can we substitute to get these other things? By doing this, I am making the problem quite a bit easier here, but let's do that first. And then if we wanted to do it another way, we can. So I would look at this and I would go, okay, arctangent is one I know. Those are the two different ways to write arctangent. So I need to figure out what's being plugged in. So here we go. I have x. There's some instructors that refuse to use this notation, and so they always write it that way. I know why they say that, but it's really hard to avoid that this notation is everywhere. So x, the sum from k equals 0 to infinity. I'm going to copy down the arctangent series. Isn't it 2x squared, not cubed? It is, but my eyes aren't very good. Oh, darn it. Thank you. Okay, so this is what we're plugging in. So right here is the 2x squared, 2x squared. Now, it is really important if you follow my advice, because I can already see in part C that we're going to need to integrate this. And if you don't simplify, you're probably going to get part C wrong. Because it's not easy to integrate. In general, if I were to give someone an integral like this, x 2x squared to the third, they might integrate that wrong. Could we go over a problem where the whole thing is squared? I think you're asking about something in particular, but let's keep going here. So I don't want to write that. I want to expand it out. So I would not write this way. In fact, in recent years, I've been encouraging students not to even write that at all, just to immediately simplify. So what I'm doing is I'm raising this to that power, I'm raising this to that power, but x squared to the 2k plus 1 is the same as x to the 4k plus 2. And normally I would have just written that on the at the beginning. So this is x times the sum from k equals 0 to infinity, -1 to the k, 2k plus 1, 2 to the 2k plus 1. And I'm going to distribute the x through. So this is the sum from k equals 0 to infinity, -1 to the k, 2k plus 1, 2 to the 2k plus 1. Why did I write a 4 here? I have no clue. X to the... Yeah, Rhea, that would be a really hard problem, um, where you had to square this. We don't square or multiply Taylor series. There was a homework question. Yeah, it's 4k plus 3. You might be thinking of the homework question about sine squared or cosine squared, but that you could do because of that identity. If you left the x on the outside, that's fine, but it will affect you in part C. Yeah. Okay, let's do the other parts. The interval of convergence is asking which known series did you use and what did you plug in? So the known series I used was the arctangent, and the thing I plugged in was 2x squared. Now, there's an interesting little discussion here, but I have found that if you just be for speed of understanding, but if you find yourself in a situation where you're having to simplify an inequality, I would encourage you, if you get stuck at any point, to just try to solve these two things. And then whatever solutions you get out of them, put them on a number line and then go back and test things out. You're allowed to use the arctangent series, yes. hmm So you can do what I did. The solutions in the archive will be a little different. The one in purple is always negative infinity to infinity. Somebody's asking, yes. But the one we used was one of these. So I say this because a lot of times the negative one bothers people because what I've seen people do is they divide everything by two and then they take the square root and this gives them an error out of their calculator and then they don't know what to do. So my comment here is it is true that there is no solution to this, but there are two solutions to this. And the two solutions are x equals plus or minus the square root. So what's confusing about this is the new inequality basically all comes from the fact that it's less than positive 1. That darn square that allows negatives. And there are three intervals that this splits it up into, but the numbers that work are here. Meaning if I plug in a 0 here, it works. So it ends up being this. I find this is one of these subtleties that most people get right and just ignore it. And so it doesn't matter, but I sometimes get a lot of questions on that. Okay, what about the last one? Find the eighth Taylor polynomial for this thing and use it to approximate. So this is one of these, use the pattern we found up here. So this one's saying find the eighth Taylor polynomial. And this was our big discussion in lecture on Wednesday, which is that means go up to x to the eighth and no further. So let's do that. Start plugging things in. Plug in a 0, plug in a 1, plug in a 2, but as soon as you get past x to the eighth, stop. So let's do this. So we're going to plug in a 0. So if I plug in a 0 over, I get 1 over 1, 2 to the 1. So I get 2 x to the third. Now let's plug in a 1 everywhere. So I get negative 1 over 3, 2 to the third, x to the seventh. Now I plug in a 2 everywhere. But wait, that gives me 11. That's too big because the question said to stop at 8. So we've done it. This is going to be 8 thirds. So right now the question is saying instead of integrating that big messy thing we had, we can integrate this instead. 2x to the third minus 8 thirds x to the seventh. And you do have to integrate it because the question asked that. So let's do this. Integral 2/4 x to the fourth minus 1/3 x to the eighth from 0 to 1. So this is 1/2 minus a third, a sixth. This answer line shouldn't say that though. Questions on this one? Yeah, if the question said to give the general pattern, so this one was specific. It was saying use the eighth Taylor polynomial. If the question was saying what's the general pattern for the integral of the thing we just had, the way it would be written is this way. You would say the integral from 0 to x of t arctangent of 2t squared dt. Give the Taylor series for that. That's actually an easier question because it's saying give the integral of this. So you copy it down exactly as written, except this becomes 4k plus 4, which may be what some people did on this problem. It leads to the same answer, but the question didn't ask for all that. And then you copy down everything else. Oops, I didn't leave enough space. So somebody was asking about that. So for the eighth term, we could look for x that has power x to the seventh. A problem like this where it says give the first few terms or give the eighth Taylor polynomial, I would just start plugging in k equals 0, k equals 1, k equals 2, and the moment I jump past 8, I would stop. So I would do exactly what I did there. You could go up here and try to think about if you wanted to try to anticipate, oh, this is going to go 3, 7, 11, 15. All right, I can stop at 7. Yeah. There were a couple other questions a moment ago. Let me look, see if I missed those. Somebody's asking about integration techniques. Um, integration would ultimately plays a pretty small role on this test. It would come up probably the most likely in double integral problems. Um, in those problems, you do substitution happens, by parts sometimes happens, and trig integrals happen. By trig, I mean like integrating sine squared or cosine squared. Um, it's unlikely there'd be any other type. Somebody's asking about a cardioid. Several different things. I have lots of private. Let me catch myself up, recenter. So we did several of these. So we've talked our way through a couple of big chunks of things. And let me just check our time. I'm in a time warp when I'm going here. Um, let's do one more object of some sort. If we have a cross product of A plus B, how would it be distributed? Did you find that on an old test? That's a very specific question. That's why I'm asking. Um, I can't remember the last time I encountered this. Um, does it distribute? I'm doubting. Um, I would want to run some examples. I should know, but yeah, you'll have to save that for the discussion board, let's say. Let's look, yeah, I like the idea of looking at a 12 or 13 question. Is there another test that was asked more than once? No, these are all kind of one-offs. Um, I do think the winter 2019 had a couple, but oh, let's just click here. Autumn 21, let's go look. Somebody asked about this in the discussion board. Again, if you go to my YouTube channel and search for a problem, you'll probably see it. Okay. Here's this multiple choice. So there's some people want to do 12 and 13. Some want to do lines and planes. Some want to do center of mass. I did do, so a comment here. I went all the way through this exam and did all of these problems in detail. You'll find that on the discussion board. Um, so like I found the equation of, was this it? No, this isn't it. Which exam was it that I did? Spring 25 I did. Let's grab something else. So spring 2024, find the equation for the plane that passes through the point and contains the line given by this, and give the x-intercept of this plane. So the moment you see those words, you want to have a plan. So let's look at that. And then, yeah, then we'll find a center of mass. But in the spring, what I was trying to say was, I do a couple center of mass questions in my most recent posts. I did one, so we can definitely do one here, but there's more. If you look at the spring 25 exam, I went through and did one. Okay, so I'm trying to find a point in a line, a point in a normal. Oh boy. They already gave me a point. It passes through the point 1, 2, 4. So I already can put that in. And now I need a normal. So there's no way around these problems. Back when we were doing this, I said you really have to think through what they gave you. And that was why I encouraged you to draw this same picture every time so you had something to attach your thinking to. Because the most important words in this problem are it contains this line. So you have to understand what that is, or we're not going to be able to finish this problem. So what does it mean for a plane to contain a line? It's very different than is orthogonal. Yeah, it means it's parallel, and even more, it means it's on there. So the word contains is another way to say on. The line is on there. If I was going to draw it, it's right here. That's very different than orthogonal. And when you read a plane equation, there's a couple facts you like to pull off right away. One fact is where are you starting? When t is 0, we're at the point 0, 3, 2. That point is on the plane because the line is on the plane. And then separately, we would like to have a vector that points that way. There's a vector we can get, and that's the direction vector for the line, 2, negative 1, 5. So this is kind of what I do is I say, well, what do I want? I want a point and a normal. What did they give me? They did not give me a normal. They gave me, let's write in words what we were given. We were given that 1, 2, 4 is on the plane. We were given that 0, 3, 2 is on the plane. We were given that 2, negative 1, 5 is parallel to the plane or on the plane. But for vectors, we tend to say parallel to the plane. So the point of me drawing that picture is to make sure I understood that's what they gave me. And then there's a plan. And the plan is always, was the normal given? And if the answer is yes, you're done. So I read through the given information. They gave me 2 points on the plane, and they gave me a vector that's parallel to the plane. So the normal was not given. So if the answer is no, then you're going to try to find two vectors that are on the plane and do their cross product. So strategy switches to find two vectors parallel to the desired plane and do their cross product. So you have to kind of have that ready to go when you're doing these problems. So I already have one vector that's parallel to the desired plane, but I need another. Yep, it's a subtract thing. So you go, all right, what do I do? Well, they gave me 2 points. So if I called this A and B, I could use those two to give me another vector on the plane. -1, 1, -2. And now we've done it. You can actually do it in either order, but we're going to do a cross product. So let's do that to review how we get cross products correct. I always lay out the whole template because that way I only have to do one multiplication at a time. So we get 2 minus 5. We get -4 minus -5. That times that. And then we get 2 minus 1, -3. This is going to be 1, but there's a negative in front of it. And this is going to be 1. And the way we check our work is this perpendicular to this? And is this perpendicular to this? So let's see. Let's do our quick check. So you check if they're perpendicular by checking their dot product. So dot product will give me -6 plus 1 plus 5, which is 0. Check. The next one will give me 3 minus 1 minus 2. The order doesn't matter in terms of finding the equation of the plane. Somebody's asking, if you switch the order, you're going to get the vector 3, 1, -1, which is not the same vector, but it still is perpendicular. It just points down instead of up. So the order just affects whether your normal is going to be up or down. But that doesn't change the equation. So at this point, you would write -3, -1, 1. If you multiply everything by -1, you get the other one. So those are both correct. So those were questions where you really had to have this game plan of, all right, what do I given? What do I want? And that's what I was trying to build back when we were doing this was this structure of thinking to help you digest the information they gave you. Where did I get the -6 and the 3? Okay, so the big fact about cross products is that when you take a cross product, it's perpendicular to both of the previous vectors. We can check if things are perpendicular by checking their dot product. So the way I got this was me checking my work. And what I was doing was -3, -1, 1, dotted with 2, -1, 5. So this was what I got. And one of my starting vectors. So if you do that dot product, what do you get? You get -3 times 2 is -6. You get -1 times -1 is 1. You get 1 times 5 is 5. If you did this correctly, then it should be 0. So I always do that, even when I'm doing it myself, not just when I'm doing it for a class. I have trained myself to always check my cross products. Because I've trained myself to do it, I usually don't write it out. I just do it with like my fingers. I hold this next to this and I go, is the dot product 0? And that makes it so I never get my cross products wrong. And then I also checked the other one. This times this is 3. This times this is -1. This times this is -1. It's 0. I find it satisfying now that I've practiced doing this. I only started it after I became an instructor, but I realized that I'm really prone to errors. So I would like to build as much into my routine to minimize errors. And if there's an easy way to check, I always do it. So that's what I was doing there. Does that answer your question? Sometimes too, you can check against the original statement of the problem. Like, does this work here? Is this actually contained on here? So meaning if I put in a 2t here and a 3 minus t and a 2 plus 5t, does everything cancel? The moment you start to get in this mode of I'm going to check everything I can check, you realize that you can check a large amount of things. Um, so the second one was the dot product of my vector with the other vector it came from. So I did -3, -1, 1, dotted with -1, 1, -2. Yeah. So basically, the moment you get done, so cross products always take me this much work. And the moment I get done, I always check if I multiply with that, do I get 0? If I multiply with that. And so it sort of closes, I've turned that into a collection of steps that I can't mess up because you have to do it so much. I've tried to build it into a thing that when I leave that work, I know it's correct. I say that, and I've still had moments where I made enough mistakes that I still got something that was perpendicular. So it's not 100% foolproof. I've been the fool before, but it dramatically catches most errors. Anyways, there were several people pushing for center of mass, and then I think we'll stop. Does somebody have a center of mass question? I will click through. A lot of times we ask those because it's a, a quick way, and relatively simple way to ask two things at once. Let me look here. I'm just flipping through looking for a center of mass. That's a center of mass. There's an extra unknown, so maybe that shouldn't be our first center of mass question we do here in this review. I think I've been through this entire one. So here we go. Let script L. That's kind of fun to look at. I write L's like this because it's in my last name. But there's a script L by the be the lamina whose shape is the triangular region with vertices this. The main thing is just to have read these so that when you see the word lamina, it doesn't bother you. Um, but they're giving me a region. A lamina is a thin sheet. Comes from the word laminate. You know, if you laminate something, it's like the veneer, the top layer. This is just emphasizing thin object, a thin layer. The reason they're worried about that is, if you had something that was a thick layer and you're trying to balance it on your finger, the thickness might affect how you're going to balance it. So the question is saying, ignore all thickness. We have an extremely thin thing, and that's a lamina. Thin plate. Okay, whose shape is this triangular region? So 0, 0, 0, 2, 1, 2, 1, 2, 0, 2, 0, 0. There we go. And I'm just going to do it now. We're going to find the equations for all the sides at some point, so we might as well do it now. Y equals 2x because the slope is 2. X equals 0 because we're on this side. Y equals 2, that's the top. We have several ways to describe that region. We could do it in terms of X, which we could talk about, or in terms of Y. To the left is 0. This would be Y over 2. Looking at them, I think I prefer in terms of Y because there's a 0 there. That's basically the problem. What I just did over there in the margins was the main part of the problem. So we'll come back. That's the stuff that has to actually do with this. You just choose one. Yep. Doesn't matter. Not for this one, it doesn't matter. I mean, if the region was a little bit worse. Okay. So now to the question. Whose density, I have a little opinion here based off of this quarter that if we ask such a question like this, that I would prefer if we gave the density function because I don't want that wording to throw someone off, but it's not a big deal. So let's say this. So the density is proportional to the distance to the y-axis. So I would feel better about this problem if we gave the density. Yeah, so the distance to the y-axis is how far you are away this way, which is what x is. So for now, let's just say that let's not get bogged down in that. I can pull up those notes so you can add this to your note sheet. But let's just for now say the problem tells you this, just so we can talk about the center of mass piece of it. So assume they tell you have a lamina. The density is K times X. What that means is it's getting heavier as you go to the right. And if you think about that, if something gets heavier as you go to the right, when you go to balance it on your finger, you'll have to put your finger closer to that side. So we have several factors at play here. If I was going to balance this little triangle on my finger, first off, it's a weird to balance a triangle on your finger, so I don't know where that little balance point will be. But in addition, it's getting heavier when you go this way in a continuous way, a linear way. One thing I really like about these problems is, yes, we're going to have to do some computations, but I have a way to check my work visually. Like if at the end of this question I get that the x component of the center of mass is at 42, I know something went terribly wrong. That's one thing I like about center of mass questions because you're probably going to know if your answer is reasonable. It shouldn't be 42 where you're going to balance this. I would expect this to be, since x goes to 1, I don't know, maybe this will be 0.5, maybe it'll be zero point 0.6. So I do like that I have that fail safe of I'll know if I really do something very wrong. Okay, so here's what you need on your note sheet. This is the double integral over the region of x times the density divided by what we call the total mass. I also don't like there's no symmetry or anything, so I think we have 3 jobs to do. So we're gonna have to compute that. The reason I say 3 is there's a total of 3 integrals in these 2 formulas. So let's go. I think I'm going to use this one to describe my region, and let's compute them. So I think I'll start with this, and then I'll compute this, and then I'll compute this. Number 1, the integral from 0 to 2 the integral from 0 to y over 2, kx dx dy. I'm going to pull the k all the way out. Let's switch to some other evaluation color. Equals k, the integral from 0 to 2, 1 half x squared from 0 to y over 2 dy. So that's k over 2, the integral from 0 to 2 of y squared over 4 dy. So that's k over 8. And now I'm going to integrate y to the third with a 1/3 from 0 to 2. That makes an 8. So the 8's cancel. K over 3. That's what this is. This is k over 3. This is k over 3. Now let's keep going. So next, let's compute. I have it green above, so let's use green. The integral from 0 to 2, the integral from 0 to y over 2 of x times the density. Okay, I'm going to pull out the k. I chose dx dy because it looked good to me. There's no reason. You could use either one. I'll tell you the reason actually I chose it is because there were 2 zeros, and to me, 2 zeros are better than 1 0. That's why I chose that. But it doesn't matter. You could choose either way. Okay, this is going to be x squared, and so when I integrate, I get 1/3 x to the third from 0 to y over 2. I got that because I had an x squared here. So then I have k over 3, k y cubed over 2 cubed dy. So that's k over 3 times 8, which I could write as 24. But now I'm going to integrate the y. 1/4 y to the fourth from 0 to 2. I'm going to plug a 2 in. That's going to be 16. And part of the reason I don't simplify is because I always like to cancel first if I can. So 16 is the same as 8 times 2, so it's k over 6. This is part of my attempt to never use a calculator. Almost always better to cancel than to multiply. Okay, so I'm happy so far. That means I know what X bar is, if I did all that right. X bar is K over 6, which is what we just computed, divided by K over 3. Okay, the K's don't matter. And now we get to test everyone's fraction skills. So my rule for fractions is to find the big bar, which is right here, and then multiply top and bottom by the same thing, whichever makes it simplest in my mind. And 6 would be the simplest because then I get 1 over 2, 1/2. Then I don't have to remember any rules about flipping things. So it turns out that x is a half, which is a little bit further to the right than I would have initially expected because it's a triangle, but it gets heavier as you go to the right. So maybe that's reasonable. Let's keep going. Third one, the integral from 0 to 2, the integral from 0 to y over 2, and this time it's going to be y times kx dx dy. Most exams we just ask for one of the values, x bar or y bar, just because usually by the time you've computed 2, you've shown your understanding. But this exam, they went for the whole thing. Okay, we're integrating with respect to x first, so I can take the y out. 1/2 x squared, 0 to y over 2 dy. So let's take that 1/2 out. And the integral from 0 to 2 of y, this is going to be y squared over 4 And that's k over 8, the integral from 0 to 2 of y to the third. K over 8, 1/4, y to the fourth from 0 to 2. K over 8 times 4. 2 to the fourth is 16. So let's cancel that 16 and we get k over 2. So then I get y bar is k over 2 divided by k over 3. And that's 1/2 over 1/3. I'm going to multiply top and bottom by 6 again. And I get 3 over 2. So there we go. X bar, Y bar is 1/2 3 over 2. Like I said, I like that I can kind of look up and see that those numbers are somewhat reasonable, that's could possibly be a place where I'm balancing this triangle, wherever it is here. That doesn't prove your answer is right, but typically if you mess up, you get something that's way off. So for me, I would rather do center of mass than something that says compute a random integral. I multiply by 6 because that's how I like to simplify fractions. So these were the two answers. I can talk about that. It's a separate thing. This was one answer. This was another. Some students learn to, what do they say? Flip and switch or something and write it this way and get a half. So that also would take you there. I have learned that the rules for flipping, I've seen students do it wrong too often. And so I've decided that I'm never going to teach any flipping rules. Also, it's fun to say that. Um, yes, that was to make it look nicer so I could interpret it. Yeah, that's all that was. Yeah, that's not necessary. But I wanted to simplify it so that I could see if it was reasonable. So that is, if you leave it unsimplified, it's just hard. On the final, this is a little different. If you're short for time, don't simplify. It's unlikely you lose points there, but I would say there's two reasons to simplify. You would like to make it easier on the grader, especially if you have time. It also gives you a chance to compute the numbers and see that they're reasonable. To me, 1/6 over 1/3 doesn't mean very much. So that's the game. So I think, just because we didn't spend a lot of time on center of mass, that doesn't mean these are bad problems. So here's another one. I was just flipping to see if I could immediately find another one. Find the mass. So the mass is just asking for that bottom part. So even though this says that this is a center of mass question, it's not really a center of mass question. It's just uh, compute the integral. So from here on out, it's going to be about describing the region, choosing your bounds. Circle of radius 2, a circle centered here of radius 2. In the first quadrant, that's outside the first circle and inside the second one. Okay, so this is not really a center of mass question. It says center of mass, but it's a polar question. So now we're going to play the polar game. We're going to find this angle. We're going to find this angle, which I already know. We're going to convert. So most of your time in these problems is spent doing this. For this one, you'll have one additional computation. You'll do the double integral of y times this x over this. And then when you're done computing this, you'll do this number divided by that number. Does it say inside? Oh no, someone caught me. Inside the circle and outside the other circle. Oh no, I misread it. It's this little sliver down here. Thank you for catching that one. Okay, I think I'm ready to call it quits. Um, find and classify critical points, draw a region and reverse the order, set up a volume. Right, yeah. Thanks for being here. So we will continue tomorrow. I hope we hit a few more things. Um, treat the final, a little differently than a midterm because you have more time. Think about ways you could check your answers. Think about ways you could check your answers against the original statement of the problem. Um, think about ways you could just share everything you know, especially if the problem looks weird in some way. Um, okay. I do have office hours tomorrow. All right, everyone. Good luck with all your other things. Let's call it a day.